In the last lecture, I introduced you to some of the contents of the universe, its stars and galaxies. In this lecture, I want to step way back and ask, how are these contents spread about on the very largest scales? In a sense, we're asking, what is the universe's topography? What is its overall structure? Now, we could ask the same question of traditional cosmologies. What's the overall framework within which creation unfolds? For example, one Hindu cosmology, there's a vast ocean beneath, and rising above, the earth and stars, and above them, realm after realm of gods, the whole contained within a giant spherical shell. It's a wonderful image. But what do we find for our modern cosmology, with its stars and galaxies? Now, I want to warn you that when you first hear the answer, it may seem a little prosaic and even dull by comparison. But I hope that you'll find on further reflection that the answer takes on a beauty of its own, and ultimately one feels things could really be no other way. So let's get started. The themes I'm going to be talking about go by the following rather technical sounding terms: isotropy, homogeneity, inhomogeneity, evolution, and the ubiquity of physical law, all of which, of course, I'll define as we go along. So let's start with the first of these, isotropy, which means the same in all directions. From Greek, iso meaning equal, and tropos meaning a turn. It seems the universe is the same at all turns, in all directions. This is potentially confusing because nearby the universe clearly isn't the same in all directions. Down is the ground, up is the sky, the sun and moon are in specific directions, and even nearby galaxies are not uniformly spread about. In order to witness the isotropy, we need to look well beyond our local, lumpy universe. We need to look at much fainter, more distant galaxies. So let's do that. Here's a picture of the entire sky, and on it are plotted the positions of 1 million faint galaxies. You can see that they're roughly uniformly spread about, though there's still quite a bit of patchiness. Now let me explain this oval shape, because we'll keep coming across it throughout this course. If you want to make a flat map of the spherical Earth, it ends up looking like this oval. Its technical name is a hammer projection. Now, the full 360-degree dome of the sky is also like a spherical shell. So when we make maps of the whole sky, they also have this oval shape. One more point. Since our Milky Way goes all around the sky and blocks our ability to see more distant galaxies, you'll often see a funny shape crossing these diagrams, like here. It's just the Milky Way getting in the way. Okay, now these galaxies are a few 100 million light years away. What happens if we go even fainter to yet more distant galaxies? Here's a deeper survey of about 10% of the sky in the southern hemisphere, showing about 2 million even fainter galaxies whose average distance is about 1 billion light years. Now you can see that the smoothness is beginning to dominate over patchiness. Now, one way to go even deeper is to use radio telescopes, like this one, to see a very unusual kind of galaxy called, not surprisingly, a radio galaxy. Now, these galaxies emit immensely powerful radio waves, so our telescopes can see them when they're extremely far away, several billion light years off, into the really deep universe. Here's a lovely image of the sky as seen by these radio telescopes. Now, don't be confused. It's superposed as a backdrop to a photo of the Green Bank Observatory shown at the bottom. Now, apart from a few large foreground radio blobs that are lying along the Milky Way, most of the radio dots in this image are these very distant radio galaxies. Okay, so here's the all-sky map showing 125,000 distant radio galaxies, and they're distributed amazingly uniformly. All right, one last example. At the greatest distance of all sits the microwave background, something we'll look at in detail in later lectures. Here's an all-sky image of this microwave glow, and it is incredibly uniform. The brightness varies by less than 0.01% from one place to another. That's less than the height of a bacterium on a bowling ball. So I hope by now you're convinced that as long as we look deep, the distant cosmic landscape, it looks the same in all directions. Clearly, the universe isn't flattened like the solar system or the Milky Way. Otherwise, there'd be more galaxies in a line around the sky. Nor is it pencil-shaped. Otherwise, there'd be more galaxies in two patches on opposite sides of the sky. No, it is isotropic, the same in all directions. Let's now look at our second global cosmic property, homogeneity. This is a term we actually use colloquially. For example, water is homogeneous, porridge is not. It's lumpy. If the universe is homogeneous, what we're saying is it's the same at all locations. Now, just like isotropy, clearly nearby the universe is not homogeneous. People, stars, galaxies are relatively dense objects with gaps in between them. It's very lumpy. But what happens when we consider much larger regions and average over them? Well, to investigate homogeneity, we're going to need distances to all the galaxies so that we can map out what their full three-dimensional distribution is. You see, those previous maps I showed you had no depth. They were just galaxies projected onto the sky. Well, in the last decade or two, huge projects, one done in Australia and one in the United States, have measured the distances to 1 million galaxies. The Australian telescope measured distances in these two strips on either side of the sky. And here they are, shown in these so-called pie diagrams. Our Milky Way galaxy is located right at the apex of these two cones, and we look out into the universe on either side. Now, I know it seems as though the number of galaxies decreases towards the edge, but that's an artificial effect, because many of the galaxies way out there, very far away, are just too faint to have their distances measured. Fortunately, it's possible to correct for this effect, and when you do that, the distribution appears uniform but patchy. Actually, you can show the uniformity fairly easily by plonking down big boxes, bigger than about 200 million light years. Now, obviously, the pattern of galaxies inside each box is different, but on average, they all contain roughly the same number of galaxies. So we say that the universe is homogeneous on scales bigger than about 200 million light years. Now, sometimes it can be difficult to grasp this cosmic quality of homogeneity because we're too used to thinking of only the local, lumpy universe. So to help you, I want you to imagine that you are a true giant among giants, over 1 billion light years tall. You would see a uniform but mottled mist of galaxies stretching out ahead and behind, to the left, to the right, up and down, and with no end in sight. Now imagine running through this mist, taking billion light-year strides, hour after hour, and all around you would look exactly the same. You would be always in the middle of an endless, uniform mist of galaxies. You see, this is the topography of our universe. There are no oceans below and realms of the gods above. There's no Dantean inferno inside or paradise outside, there is a uniform mist of galaxies stretching off in all directions, apparently without end. Now, at this point, I'd like to clarify a possible source of confusion, because in the last lecture, I explained how astronomers witness the universe as a set of giant spherical shells, with more remote shells containing ever younger galaxies, with the most remote shell being the Big Bang itself. And this doesn't sound much like the homogeneous universe I've just described. But don't forget, the view of nested shells is only what astronomers witness, not what there actually is. The finite speed of light means we cannot see the full homogeneous universe as it actually is now. Instead, we are forced to see more distant regions as they were in the past. This homogeneous universe is how things really are, not how we see them. Now, let me return to the example of water as a homogeneous substance. See, if you look at water on scales below a few nanometers, it becomes lumpy. There are molecules here and there. It becomes inhomogeneous. Now, the universe also has this dual quality. Remember, it's patchy and lumpy on scales less than 200 million light years, and it's smooth and homogeneous on scales above 200 million light years. See, in water, the transition scale is about a nanometer, while for the universe, it's about 200 million light years. This is a fascinating property of the universe, and it's going to be a very important part of our cosmological story to explain that transition and why it occurs at 200 million light years. But you'll have to wait till lecture 17 to find out the answer. Now, these qualities of large-scale isotropy and homogeneity are sometimes rolled into a single idea called the cosmological principle, which states that the universe looks the same statistically at all locations. Actually, I should say that differently, from all locations, where statistically means as long as we average over large enough volumes. Now, although today we can more or less demonstrate the truth of this principle, when it was first introduced in the 1920s, it was a pretty bold assumption with little supporting evidence. But it was introduced for two rather different reasons. One was purely pragmatic. It was a simplifying assumption that allowed progress to be made with mathematical descriptions of the universe, like the ones we'll meet in Theme 2. Not surprisingly, if you assume the universe is homogeneous, it simplifies things enormously. But there was another motivation for adopting the cosmological principle, an aesthetic one. Basically, it embodies a principle of deep egalitarianism. Every location in the universe is equivalent to every other. There are no special places. Astronomers often refer to this as the ultimate post-Copernican viewpoint, because it was Copernicus who first argued against a geocentric cosmology in which the Earth occupied a special central location. In fact, ever since Copernicus, our special status has continued to slip away. In the 1920s and 30s, it was discovered that the solar system wasn't at the center of the galaxy, and that the galaxy wasn't at a particularly special place. It was an unremarkable, ordinary location. So any view that renders us average is said to be a post-Copernican view. In a sense, the cosmological principle is leveling the playing field. Not only is our location not special, nowhere is special. Everywhere has the same status. Now, this aspect of the cosmological principle addresses two very common but infamous questions. Where's the edge of the universe into which the expansion is going? And where's the centre of the universe where the Big Bang took place? But if all locations are equivalent, the universe can have no edge, since a galaxy at an edge would certainly be in a special location. Galaxies one side, none on the other. At first sight, it seems as the only way to achieve an edgeless universe is for it to be infinite. But in Lecture 10, we'll learn that the universe might be subtly different, having what cosmologists call spatial curvature. Now, without going into details here, you can get a feel for this by imagining standing in an enormous forest. The nearby trees are the nearby galaxies. Looking out, all around, it looks the same. It's isotropic. You could walk for hours in any direction, and the forest would be the same. It is homogeneous. But now imagine that the forest covered the entire spherical surface of the Earth. Would you ever come to the forest's edge? No, you wouldn't. The surface of the Earth is curved and finite. It's in this sense that the universe might have no edge and yet be finite. Also, you can see that no place in the forest is central. Each location is equivalent. And if the Earth were expanding to mirror the cosmic expansion, then all trees would simply separate from each other. There's no central tree from which all others are receding. Now let's turn to consider a very interesting possible extension to the normal cosmological principle. It's called the perfect cosmological principle, and it adds time to the mix. Not only would the universe appear the same from all locations, it might also appear the same at all times. Now, if the universe is the same at all times, it's in a sort of steady state. And so the theory that explores this possibility is called the steady state theory. And it was famously promoted in the 1950s and 60s by three cosmologists, Fred Hoyle, Hermann Bondi, and Tommy Gold. Now, the steady state theory disagrees with the Big Bang theory for the simple reason that if there is no change, the universe must be infinitely old, with no beginning, no Big Bang. Now, this, to Hoyle at least, felt more perfect in some philosophical sense. To him, the Big Bang was a rather messy affair, somewhat unworthy of the universe. In fact, we owe the rather graceless term Big Bang to Hoyle, who coined it to sort of gently deride his opponents during some public lectures broadcast in 1950 on the BBC. Now, you may be wondering how the steady state theory copes with expansion. After all, won't the universe just get emptier and so change? Actually, no. The theory doesn't require everything to be frozen and static. The idea is that as the universe expands, new matter is created, which ultimately makes new galaxies, which fill in the widening gaps. Now, one of the great virtues of the steady-state theory is that it is testable. Since it demands that the universe is unchanging, all we need to do is to look far away and therefore back in time. Do things look different out there back then? If they do, the universe is changing, and the steady-state theory and the perfect cosmological principle cannot be correct. Now, back in the 1950s, this was easier said than done. The optical telescopes were much less powerful than they are today, and they couldn't really see far enough. So the first efforts to look for change in the universe used radio telescopes to see those distant radio galaxies I showed you earlier. But still, it wasn't easy. These radio galaxies were too faint to actually measure their distances. So radio astronomers had to come up with a different method that used only the brightness of the radio galaxies. Here's the basic idea. As we saw a minute ago, if you look at a patch of sky with a radio telescope, there are many radio sources present. Now, a few are bright, but many more are faint. The critical question that this method asks is, as I include fainter and fainter sources, how does their number increase? If I include fainter sources, then I can see these radio galaxies out to greater distances. And so I include a larger volume, and so there are more of them. Now, as long as the distribution is uniform and unchanging, then it's fairly easy to show that you should find this straight line on a graph of source brightness against number of sources counted. As you look at fainter and fainter sources, you count more and more. And the line increases with a famous slope of -3/2. One of the first groups to use this method to look for cosmic change was headed by Martin Ryle at the Cavendish Laboratories in Cambridge, only a mile from the department where Fred Hoyle worked. So these early years are now seen in the history of science as a classic case of how personal conflict became interwoven with a very important but very difficult scientific experiment. There were actually a number of problems with the first surveys in the 1950s, and the results were genuinely unclear. But by the mid-1960s, most of the problems were ironed out, and the data gave a pretty clear message. Here's the original data. There were more faint radio sources than predicted by the -3/2 law. So the density of radio galaxies was higher at larger distances, and therefore higher at earlier times. And this was evidence for systematic change in the content of the universe. In the past, it was richer in radio galaxies than it is today. It's this kind of systematic change that undermines the steady-state theory. If the universe is changing, it's clearly not in a steady state. The perfect cosmological principle, while philosophically appealing, does not seem to apply to the real universe. Well, let's bring this topic up to date. There is now overwhelming evidence for change in the universe, what cosmologists often call evolution, though, of course, that's not a Darwinian term. Perhaps a better term would be development. Here, for example, is another pie chart. Now, this one spans almost the entire visible universe. The edge is almost 14 billion light years away, almost 14 billion years ago. The dots, in this case, are objects similar to radio galaxies called quasars, and you can see how rare they are nearby today compared to far away long ago. When you correct for the difficulty of finding distant quasars, you get this graph that nicely shows how the population of quasars grew rapidly after the Big Bang, had a heyday around 3 billion years later, and then has steadily declined to today. Turning to different lines of evidence for cosmic change, in Lecture 4, we'll see that the rate of cosmic expansion has changed in time. In Lecture 19, we'll discover that distant galaxies appear systematically younger than nearby ones. In Lecture 21, we'll find that galaxies were less clustered in the past. And most dramatic of all, in Lecture 13, we'll find that the million-year-old universe didn't even have any stars or galaxies. It was just a hot, thin, glowing gas. The steady-state theory and the strong, perfect cosmological principle really are no longer tenable and haven't been since the late 1960s. The universe really does evolve. Now, I'd like to close this lecture with 4 somewhat more reflective comments. First, we've learned that the distribution of matter in the universe seems deeply symmetric. It's isotropic and homogeneous on large scales. How did this come about? What expanding seed might cause matter to be distributed so smoothly and symmetrically? Well, what things are innately isotropic and homogeneous? No form of matter has this character. It's all of particulate form. It's lumpy. But space is inherently isotropic and homogeneous. Perhaps a kind of expanding space was converted into the matter that now fills the universe. As we'll see in Lecture 30, this is exactly the idea behind the theory of inflation. My second point is to stress that homogeneity doesn't just apply to matter, but also to the laws of physics. When we look out into the distant universe, we find the same laws of physics that work right here on Earth. We see galaxies rotating, so gravity is the same. The galaxy light contains emission and absorption lines, so atomic and quantum physics are the same. There are similar types of stars, so nuclear physics is the same. One might call this the ubiquity of physical law. But unlike matter's homogeneity, which is only evident on large scales, the laws of physics are identical from 1 nanometer to the next. Now, quite why this is true isn't fully understood, but our best theory, called quantum field theory, suggests the answer is rooted, once again, in the properties of space itself. My third point is that the perfect cosmological principle reminds us that we need to be rather cautious when using aesthetic or philosophical arguments to guess how nature works. Now, sometimes our sense of beauty and perfection works very well. For example, Einstein's special and general relativity theories both emerge directly from deep symmetry principles. And much of modern particle physics also rests on symmetries within nature. But there are counterexamples. Aristotelian physics and the Ptolemaic model of the solar system drew heavily from a sense of how things should be. For example, the primacy of the circle as a model for all celestial motion. And much of this just turned out to be plain wrong. So too with the perfect cosmological principle. Hoyle felt the universe would be more perfect if it remained forever unchanging. But the universe does change. And the Big Bang really seems to have happened, despite at least Hoyle's preference for it to be otherwise. Finally, let's think again about what the cosmological principle means emotionally. See, often in traditional cosmologies, the more remote we travel from home, the more different and alien the environment seems to us. Realms of the gods, a surrounding fire, or even void. See, it's not that way in our modern cosmology. Go to a location far, far away, well beyond our current 14 billion light-year horizon, and what would you find? Exactly the kind of universe we know so well, filled with atoms, planets, stars and galaxies, behaving in exactly the same way. Looking far out into space, we would see younger galaxies, and beyond them, a microwave background. This, I think, is a wonderful realization. Rather than feel the anxiety of wandering ever further from home into ever more alien realms, we find that home is everywhere. We are really at home in the universe. We can feel familiarity and connection with the entire universe, because what we find here, all around us, is ultimately all there is.